Okay, good morning. I'm Ibrahim Ogunsanya. I am the last PhD student of Professor Hansen, so very honored to be here. I will be showing her some of the work that we've always discussed about, but I haven't had the opportunity to actually carry out, which is the pitting resistance equivalent number of stainless steel. So I'm glad that Birkin organized this in a way that Rick, comes before me, because he actually placed stainless steel in a position that makes it easy for me to justify or talk about, I guess. So this is the same bridge, all right? So we know, two bridges, one lesson, which is essentially cost, overall cost, initial cost, whichever one you prefer, to go about. But my work here is to look within the stainless steel family itself, as opposed to, cross, group with other corrosion-resistant material. So the hidden vulnerability of stainless steel is that it's not immune to corrosion. I think the last questioner, sort of raised something like that, but it's not immune to corrosion. It's very corrosion resistant, and we've actually done a lot of corroding, of that in the lab. This is with cracked concrete, by the way, so it's not, so transverse and longitudinal cracks, but it's not immune to corrosion. Now, looking beyond the coastal area where, 3% chloride, just looking at anti-ISA, because it's a lot more aggressive, at least in Ontario. So we put up to 21%, or you can see from there 24.5% in some cases. And it's not just the chloride also I wanted to point out. It's also including the cations that are attached to the chloride, because some of them are more aggressive than others. So that's something to actually, point out. So, and you can have this type of problem, the durability itself, the safety for the drivers and all that. So the justification for using stainless steel cannot be, said without looking at the cost, and we're talking about the alloying composition for the most part, many of which are expensive, from the molybdenum to, nickel to chromium and then manganese afterwards. So it's, how much is optimal? Did we actually design this stainless steel for, the high pH, or did we take knowledge from the superiority in acidic environment, etc.? So this is something that we wanted to look at, in our work. So to assess stainless steel, either you're trying to, make a new one, or you're trying to find out which one should you use, as you went for the Champlain Bridge, looking between, the duplex 2304, 2205, and other types of stainless steel. So to make that decision, it takes a lot of experimental work, and you're able to get valuable electrochemical results, but you're also able to get long-term results as well, so which is good. But the challenge is it is resource consuming, and it's very destructive, obviously, like any other test. And it doesn't help you with timely decisions, either you're bridge manufacturers or the users of the stainless steel to begin with. So that's something we wanted to look at. So we wanted to give a very simple way to assess the resistance of stainless steel within the stainless steel family, by the way. So we wanted to look at that and see what way we can help, improve that or solve that problem. As I've said, experimenting pitting resistance of stainless steel takes a lot of time. This is some of the work that Professor Hansen has been involved with. I think accidentally, Rick also showed the same work, actually. So this takes 850 days of assessment. So that's a long time, just to look for the better rank stainless steel. There's another one on stainless steel, but clad this time. That took 1,500 days. So that's a lot of time, just to make, again, a decision on stainless steel. So we're looking at something that exists but doesn't actually work, for the concrete environment, which is a pitting resistance equivalent number. So it's a tool, it's a non-destructive assessment tool. And you can see on your left side, I believe, yes, you can see that it is made with what we call a CPT, which is a critical pitting temperature. Which is used for assessing stainless steel. And that formula at the top of that left-hand side also was created based on chromium, molybdenum, and nitrogen, and some other, alloy later on. So the benefit is that it is non-destructive, it is time and, cost-effective, for decision-making, which actually works. and it can help you rank your stainless steel very, very quickly, and it supports the development of new grade if you're a rebar manufacturer and then looking to, make a new ones. However, the challenge here is it is developed based on electrochemical property, but which one? As I've mentioned, that was developed based on critical pitting temperature, which is a high temperature of 350 degrees and all that. And it's also developed based on some specific alloying composition. And if we're trying to solve the cost effectiveness of stainless steel, we need to look at the expensive alloys, molybdenum, nickel, etc. The other thing is it doesn't actually capture our exposure environment, so the current PREN number is not going to work. So looking on the right-hand side is what we're proposing. So as I've said, the existing one is acid to neutral environment, 300 to 400 degrees Celsius temperature. And we're proposing something that actually fits for the high pH as opposed to neutral environment, so 12 to 14 pH between, and presumably lower too if time permits. I'm not sure how long this work is going to take. And more importantly, exposure to deleterious species such as chloride and sulfate. We're also looking into developing the PREN formula based on parameters that we actually test in the lab. So not critical pitting temperature, but your typical corrosion potentials, corrosion current density, pitting potential and pitting current, as opposed to that. So what we did was a very small test. By the way, we try this, in case you're wondering, on literature data at the moment is very erroneous. So we're going with our experimental data. So what we did was to perform a potential dynamic polarization and, got the data from there, which the curve you can see at the top there. So our input parameters were focused mainly on the chromium, nickel, molybdenum, and manganese, and then as well as pH. We varied the pH and then chloride content as well. So we took that data set and put it into some regression model on machine learning, and then we basically developed the PREN. We developed a PREN index based on that and a user interface that people can use. Just looking briefly on the experimental data, this is very straightforward if you're looking from one grade to the other, if you're looking from increasing chloride. So the curve you're seeing is corrosion current density versus corrosion potential. So what you see is an increase as chloride is increasing chloride, as you go from 0 to up to 24% chloride, in solution, which is a lot and nothing close to what carbon steel can withstand. Now, similarly, we're looking at pitting potential and pitting current density. Similarly, what you're seeing is an increase in chloride with a decrease in pitting current density, pitting potential as well, sorry. So what we did is take those data and split it up into something that represents the alloying composition, so chromium, nickel, molybdenum, manganese, pH, and chloride, and then we're trying to extract the output from that. So having a look to just sort of see the influence of chromium, nickel, molybdenum, manganese. It is much straightforward to look at the pH and the chloride because you can see an increasing and decreasing trend, which is something that you're familiar with. As pH increases, you're having your corrosion potential becoming more positive, which is good. And as chloride increases, you're having your corrosion potential becoming more negative. So that's something very familiar. However, the alloying composition is neither here nor there. So it is somewhat clear for corrosion when you look at chromium. You have a decrease in trend after, 17% chromium content. Before that, you have more positive, and then on average, and then after that, you have more negative, which is suggesting that there's no much benefit for the high pH environment that we're using stainless steel, increasing the chromium content beyond 17%. Nickel, again, plateaus somewhat, if I can say that, at between 4%. Again, and then molybdenum, again, does the exact same thing. Actually, this goes the opposite way, becoming more negative, actually. And then manganese follows the same trend as molybdenum. Now, the difficulty here is isolating each of these elements. So it's take it with a grain of salt, but it's just to show you the concept that we're going with. So corrosion current is much more very similar for all of them. They go in a straight line, no increasing majorly or decreasing trend. But again, similarly, it's clear for pH and chloride. If you look at pitting potential, something similar. If you look at pitting current density, it's the same. So, but these are experimental data based on commercial stainless steel alloy, which is very difficult to isolate the chromium from the molybdenum, from the manganese. Just repeating that so that it can become clear what the challenges were. So we basically developed a model which is based on predicted E-core, which is corrosion potential, current density, pitting potential, pitting current density. So you can see that trend there, which it aligns. We set up some data for training and testing. And this is the developed PREN number, which goes in the same fashion. But the takeaway from that, not to bore you with the previous slide, is what is more important. Now, this is telling you, what I like about this slide is it's telling you that if you do experimental data and if you based your result, your ranking of your stainless steel, I'm not sure if this pointer works. It's the red one? Yeah. So if you base your ranking on E-core, you will find nickel and manganese to be more sensitive to that ranking. If you base it on I-core, manganese is a lot more sensitive to that. If you base it on pitting potential, nickel and manganese is more sensitive, so things like that. So the same thing goes for chloride and pH. So E-core, chloride is more sensitive to E-core, I-core, E-pit, and then pH. So which means when we're ranking stainless steel in the lab, it's important to know what the ranking is based on, rather than this takes first, second, or the third. So that's the importance of that. So this is the PREN formula that we come up with based on the formula derived at the top. What we tried to do was take a linear a regression model that is not going to be complicated. Obviously, the data could be improved with other types of model, but we want something that can give equations out, just like the existing PREN number, so that there won't be any, complication as regards its use. So when you look at that PREN formula, so we developed PREN formula based on E-core, based on I-core, E-pit, and I-pit, because, like I said, all the stainless steel and the alloy composition, they're very sensitive to either of them. So it was important to develop, 4 different types. I mean, the existing one has 2 different types on duplex stainless steel and austenitic stainless steel. So it's not impossible to have more than one PREN formula. So if you look at, we had an overall ranking. We used it for a case study in pore solution, pH of that, and 24% chloride addition. This would be the overall ranking when it comes to that. And if you use that with the existing PREN number, you can see that there's some positional change as opposed to which one ranks first, second, or third. So 24-100 consistently ranked lower. But like I said, if you're testing 24-100 in the lab, some of the work that Rick showed earlier, you will see that sometimes 24-100 may actually have a high PREN number in some cases if you're judging by the pitting current. So it depends on the criteria that is used in the lab, to make this decision. So that's what that is saying. In conclusion, the overall ranking of based on the commercial grades of stainless steel is that, with the duplex 2204 ranking first, the 304 molybdenum free ranking that, and then 24-100. One thing we find about the 24-100 is, in this case, it's completely manganese based with no nickel, so there needs to be some nickel balance to actually improve its corrosion resistance. So you can see that, again, like I mentioned, it's very sensitive to E-pit, so the position changes depending on what you're looking at. Certain alloying elements, do not show beneficial effect beyond some threshold. So it's important to actually look within the stainless steel family and see how much cost-effective stainless steel can be built with that knowledge. Corrosion resistance is multifactorial in nature, which means nickel and manganese influence that, and then chloride and pH influence this, so it depends on a lot of factors, essentially. So the PREN number that we're looking at, we're basically concluding that it must account for the cementitious system and the exposure factors. So in this case, what we represented our cementitious system with is just change in pH. We understand that using mortar, concrete, that would change. Exposure factor, we're simply limiting it to chloride and sulfates in this case. So obviously, with other models, things can be improved, but we considered other models, they don't have an equation to give. It's just a tool, so we will need something that, can be taken anywhere as opposed to something that can be seen on a website. So that's currently what we have. The current work is still ongoing. Mohi here, my PhD student, we're building different stainless steel alloy we're casting them with an induction melter to vary the content. So we're actually trying to improve that. And we're not only going to be looking at the 4 criteria that we're looking at, we're also going to be using some local electrochemical testing, scanning electrochemical microscopes, SKPs and all that to basically determine the knowledge on the stainless steel. And we're also going to take into account the spatial electrochemical parameters on that surface as well, which is certainly currently in our lab attached to the current equipment. And then finally, I just wanted to show some of our shared moments with Caroline. This was enjoying a barbecue, and this was in the office trying to make sense of some, I think, Moshotsky data. I don't remember exactly what it is. It took 3 years, and then some fun times in award and all that. So anyways, thanks very much.